Hello everyone, and welcome to some more remote learning. Today for Calc 2, we're going to be going over the dot product. What is the dot product and what exactly is it used for? Those are our two big questions that I want to get answered in this worksheet. Well, first of all, it can help us find the angle between two vectors. It can help us find the projection of one vector onto another. It's a quick way for knowing if two vectors are orthogonal, and it also shows us the work done by a force. Although the work part is more about the application based of the dot product, so I won't get too much into that on the worksheet. However, we will get into all those other topics with the dot product. But for now, let's go over a quick definition. So the definition of the dot product is, given two vectors, vector u and vector v, their dot product is, that's vector u dotted with vector v, that's going to be equal to the magnitude of vector u times the magnitude of vector v times the cosine of theta, where theta is that angle between those two vectors, and it's going to be between 0 and pi, including those bounds. And quickly, I want to note that u and v for this definition are non-zero vectors, and this holds true for 2 dimensions and 3 dimensions. The result, that dot product, is a scalar. I cannot emphasize this enough. The dot product between two vectors is a scalar. And if you're confused on what a scalar is just some real number. So when we do the dot product, our output is not a vector. Our output is just a number. So before we go getting that output, let's talk about representations of u and v, those vectors, for a couple different cases. For example, if we're looking at our definition, u dot v, that dot product, is going to be equal to the magnitude of u times the magnitude of v times the cosine of theta. Well, if you remember back from calculating the magnitude of a vector, the magnitude is the square root of those individual components of that vector squared and summed together. So if we're squaring those individual components, then we're only going to get positive numbers. So the magnitude of u is going to be positive, and the magnitude of v is going to be positive, because the magnitude is just the length. So if the magnitude of u times the magnitude of v is positive, for this first part, whether or not u dot v is positive all depends on cosine of theta. Because if the magnitudes are positive, in order to get a number greater than 0, then the cosine of theta also has to be positive. So all we have to ask ourselves is, well, on the interval between 0 and pi, when is the cosine of theta positive? Thinking about a unit circle from 0 to pi, so that upper half, cosine is positive from 0 to pi over 2. Not including 0 and not including pi over 2, but between those, cosine of theta is positive. So that means my angle is between 0 and pi over 2. And if I'm to draw that, here I'll put vector u, and here I'll do some vector v. You can see that angle in between there, the cosine of that angle theta is going to be positive. So when our dot product is greater than 0, that's going to be some acute angle. And just quickly, and notation wise, I want to note that putting u and v in bold is also the same thing as writing that with vector notation. So those bold letters also represent a vector. So now, continuing on, we have to see, okay, so the magnitudes are always positive, so the only thing that makes this dot product less than 0 would be if the cosine of theta is negative, which, if you remember from that unit circle, that's going to happen over here in that second quadrant. So between pi over 2 and pi, because remember, we're only looking at that upper half. So if you think about drawing vectors like that, then if this is vector u, vector v will form an obtuse angle. So it'll be an angle that's greater than 90 degrees. So I'll quickly label my vectors for you so that you can see. Here's u, v, u, v. And now, looking at u dot v, if u dot v is equal to the magnitude of u times the magnitude of v, that means that this was multiplied by what number? It was multiplied by 1. So we just need to ask ourselves, when does the cosine of theta equal 1? And that's when theta is equal to 0. So if the angle in between those is 0, that means that vector u and v, so here will be vector u, that angle between them is 0, which means they point the same direction. So right on top of that would be vector v. Now the next one, when u dot v equals the opposite, so that negative magnitude of u times the magnitude of v, well, that would be multiplying by a -1, right? So when does the cosine of theta equal -1? Well, think about that unit circle. That's when theta is equal to pi. So u and v will be pointing the exact opposite directions. So there's my vector u, and there's my vector v. And it might be helpful to draw these different colors so that you can see where the vectors stop and end. But because we're not worried necessarily about the length, just more so the direction, it's fine for now. So our last one is u dot v equals 0. And this is definitely an important one to remember, so I'll go ahead and rewrite it down here. U dot v, those vectors dotted together, equals 0. If that's the case, that means that the cosine of theta has to equal 0, which between the interval of 0 and pi, that occurs when theta is equal to pi over 2. So 90-degree angle between those vectors. So here's my vector u, and here will be vector v. And the angle between them is 90 degrees. And that leads us right into our next part. Orthogonal vectors are when two vectors, u and v, they are orthogonal if and only if u dot v is equal to 0. In the case of the 0 vector is orthogonal to all other vectors, and in 2 dimensions or 3 dimensions, those orthogonal vectors, the other word for that is perpendicular or normal. So when we're saying orthogonal in 2 dimensions and 3 dimensions, we're talking about that it's perpendicular. And that's the case when the dot product equals what? When the dot product equals 0, those vectors are orthogonal. So let's go ahead and jump into example 2. In example 2, it says compute the dot product if u is a unit vector and v, that magnitude, is equal to 2 and the angle between them is 3/4 pi. So let's just rewrite our definition. U dot v is going to be equal to the magnitude of u times the magnitude of v times the cosine of theta. So u dot v, well, even just thinking about from those pictures above, 3 pi over 4 is in that interval between pi over 2 and pi. So we know we're going to be dealing with an obtuse angle, which is going to be a negative dot product. So I know I'm going to have some negative number as my dot product. And remember, a dot product is a scalar. So now I just have to plug in the magnitude of u, and it gives us the magnitude of v. But in fact, it also tells us that length of u because it states that u is a unit vector. A unit vector has a length of, hint, 1 unit. So a unit vector has a magnitude of 1, and we're multiplying that by 2, and that will get multiplied by the cosine of 3 pi over 4. 1 times 2 is 2, and the cosine of 3 pi over 4 is going to be negative root 2 over 2. So our dot product of u and v is a negative root 2 in example 2. Now, in order to use this definition of the dot product the way that we've been using it, we would need to know the angle. which a lot of times the angle is either hard to calculate or maybe it's unknown. Or maybe we're even solving for that angle. Well, there's a different definition that we can use for the dot product to help us get there. So the other definition is, given the two vectors, we're still going to stick with u and v, we're breaking them up into their components. u1, u2, u3 for vector u, and v1, v2, v3 for vector v. The dot product between those two will be u sub 1 times v sub 1. And I'm not going to use a dot here so that it doesn't confuse you. These are just multiplied together. So u1 times v1 plus, now we're going to do our second components multiplied together, u2 and v2. And then we're going to add that to our third components multiplied together, u3 and v3. And note, this is u dot v. That is going to give us the dot product. So if you think about using this formula, we're multiplying two numbers together, adding them, multiplying two numbers together, adding them, multiplying two numbers together. If all of those are getting added together, again, this is just a number, so it's a scalar. So now that we know this other definition, let's jump into example 3. Let's compute the dot product of the given vectors in A and B, and then we're going to find the angle between those two vectors. So if I'm computing the dot product between u and v, well, I'm not given an angle between them, so a good place to start is with this definition above. So I'm going to take 1/2, which is my first component, and multiply it by 1. So 1/2 times 1 plus my second component, which is root 3 over 2, times the second component in vector v, which is 0. Now, unlike above, I'm not working with 3 dimensions. I don't have a u3 or a v3. I can stop my dot product here because it works in 2 dimensions as well. So 1/2 times 1 is 1/2, and root 3 over 2 times 0 is just 0. So I have 1/2 plus 0, which equals 1/2. Now remember, this is the dot product between u and v. I have the dot product now, but I also need to find the angle between them. Well, how exactly do I do that? Think about this. We know u dot v, and we can easily calculate the magnitude of u and the magnitude of v, and knowing that, we'll be able to solve for the cosine of theta, which in turn will allow us to find theta. So let's just divide u dot v by the magnitude of u times the magnitude of v. Doing that will leave me with the cosine of theta. So let's go ahead and calculate those magnitudes. Well, the magnitude of u is going to be the square root of 1/2 that quantity squared plus the square root of 3 over 2 that quantity squared, which is going to be 1/2 squared is 1/4 plus square root of 3 over 2 squared is going to be 3 over 4. And that's going to be the square root of 1/4 plus 3/4 will be the square root of 1, which is equal to 1. So I know that my magnitude of u is 1. So right now, for u dot v, I have 1/2, and I'm going to be dividing that by, well, my magnitude of u is 1. I just need to multiply that by my magnitude of v, which v is already a unit vector because the square root of 1 squared plus 0 squared is 1. So I know that my magnitude of v is also 1. So 1/2 divided by 1 equals the cosine of theta, which means that 1/2 is the cosine of theta. So we have to think, go back to a unit circle or the triangle method if you learn that way. What is theta that gives us the cosine of theta equals 1/2? And that's going to be that theta equals pi over 3. So that's our angle between those two vectors. And as a good double check, remember, we got that the dot product was positive, so our number should be between 0 and pi over 2, which it is. So our dot product is that scalar of 1/2, and our theta is pi over 3, or 60 degrees. Now let's go ahead and jump into B. In B, we have the vector 3, 4, -1, and 2, 0, 6. So we're going to be dotting u and v. And this time we're in 3 dimensions because we have 3 components in those vectors. So we'll do 3 times 2 plus 4 times 0 plus -1 times 6. So this is going to be 6 plus 0 minus 6, which equals 0. So our dot product equals 0, and right away from that, when our dot product equals 0, that means our vectors are orthogonal, which means that theta is equal to pi over 2. Those vectors are perpendicular. Now let's jump into a little bit more with dot products, because remember when we started this video, I said that the dot product could help us find the angle between 2 vectors. It was a quick way of knowing whether the 2 vectors were orthogonal, and there were 2 other things I had mentioned. The amount of work done by a force, which work is that dot product between your force vector and your displacement vector. But one thing I do want to go over is the orthogonal projection of some vector u onto v. What exactly is that orthogonal projection? Well, that projection will tell us how much of vector u goes or points in the direction of vector v. Lots of times I like to think of orthogonal projections almost like a shadow. So if you can envision, here is our light shining down. I have some vector v, I'll make in green. That's what I'm going to be shining on to. And vector u is what I'm shining. Well, if you can envision the shadow that that would make, u onto v, so again, u is blue, and my vector v I made in green, that shadow would be this vector here. That vector, that new vector, is our projection. So you can envision that if u was perpendicular to v already, then there would be no shadow, so that projection would be the 0 vector. Or if my angle between those two and I was doing this projection, then my shadow is going to be in the opposite direction of v. So my projection would be in the opposite direction of v. So when we're dealing with an acute angle or an angle between 0 and pi over 2, we're going to be in the direction of v. When it's obtuse, it's going to be in the opposite direction, and that projection will be the 0 vector if u and v are perpendicular. But let's go into the formulas behind all of this. So the orthogonal projection of u onto v is written as the projection of whatever you're projecting, so this will be vector u, and then the projection will have a sub of v because we're projecting u onto v. Now the formula for this is going to be the magnitude of u times the cosine of theta times v over the magnitude of v. So essentially the unit vector of v, because we want either that same direction or, depending on if cosine is negative, that opposite direction. So v over the magnitude of v is just a unit vector, which means that the magnitude of u times the cosine of theta, that's going to be the magnitude of our projection. Because if the magnitude of this unit vector is just equal to 1, when I'm taking the magnitude of the entire thing, that magnitude of u times the cosine of theta is what dictates the actual magnitude of my projection. And that's also known as the scalar component of u in the direction of v. So again, this is scalar, S-C-A-L, and it's going to be of u onto v. That is that magnitude of u times the cosine of theta. So think about it. If this is a unit vector and we're multiplying it by some scalar component, so some real number, the projection is going to be a vector, whereas the scalar component is just going to be a number. Another way to write this scalar component would be vector u dot v over the magnitude of v. So there we go, using that dot product again. Or as opposed to using that magnitude of v at all, we can simply do dot products and multiply it by vector v. So another formula for the projection would be u dot v over v dot v times vector v. So again, dot product, which is a scalar, over a dot product, which is a scalar, scalar divided by a scalar, is still some number, so some scalar, but we're multiplying it by a vector. So the projection is a vector, whereas a scalar is just a number. So there we have a couple different ways, or a couple different formulas for finding projection and scalar. So let's actually apply these now. So in example 4, we have parts A and B where we're going to calculate the projection and we're going to calculate the scalar. Now I don't know the angle between these, I don't know that cosine of theta, so I'm going to shy away from using that formula. However, I think it'd be pretty easy to use this formula to find the scalar, and then I can multiply that by the unit vector of v, or I could start with finding my projection and then find the magnitude of my projection to get my scalar, because my scalar is the magnitude of my projection. So let's do it that way first, just to show you. So my projection of u onto v, I'm going to do u dot v over v dot v multiplied by vector v. So my dot product of u and v, taking those first components, that's going to be 2 times 1 plus, now taking my second components, 4 times 0. And that's going to be all over v dotted with itself. So that's 1 times 1 plus 0 times 0. And that all gets multiplied by vector v, which is 1, 0. So 2 plus 0 is 2 over 1 plus 0 is 1. And that gets multiplied by my vector 1, 0, which multiplying that through gives me vector 2, 0. Which totally makes sense for this problem, even if we were to visualize it. Because if you think about, if I was to draw some xy plane, I have my vector v, which again, I'll do in green, that's 1, 0. So 1 in the x and 0 in the y. So I have some vector, if I'm starting at the origin, that looks like this. And then my vector u is 2 in the x and 4 in the y. So I'd go 2 over and 4 up. So some vector like this. But think about that. This was at 1, and then I went over 2 to draw my blue vector. My vector v is only in the x direction. So if you can envision shining that light down, my projection is going to be how much that vector goes in my x direction, because there's no other part of that vector besides that x component. So that's going to be 2. But it's not going to be necessarily that easy to visualize. It's really only this easy when our vector only has one non-zero component, because then u in that direction is just the amount that that same component is. So that's that 2, 0. That is that projection. So what's the magnitude of it? Well, it's got a length of 2. So I know that that scalar, the scalar of u onto v, is equal to 2. Because remember, that scalar is just the magnitude of our projection. Which, if you want to double check, what's u dot v over the magnitude of v? Well, v is a unit vector, so the magnitude of it is 1, and u dot v, remember, was 2, because 2 times 1 plus 4 times 0 was 2, and 2 divided by 1 gave us 2. And again, this one works out so nicely because v is a unit vector and it only has one non-zero component. Let's do one a little more difficult. Let's do one with 3 dimensions, the projection of u onto v. And this time, let's do a different formula. Let's first find our scalar, and then we'll take the scalar and multiply it by the unit vector of v. Because remember, that scalar is the magnitude of u times cosine of theta. So if I use this formula instead, I'm going to get that same result. So u dot v over the magnitude of v is our scalar. So let's first find our scalar. So again, u dot v over the magnitude of v. U dotted with v will be 5 times negative 1 plus 1 times 1 plus negative 5 times negative 2, and that's going to be all over our magnitude of v, which is the square root of negative 1 squared plus 1 squared plus negative 2 squared. So if I'm to simplify this down, 5 times negative 1 is negative 5, plus 1 times 1 is 1, plus negative 5 times negative 2 is a positive 10, and that's all over the square root of 1 squared, which is 1, plus 1 squared, which is 1, plus negative 2 squared, which is going to give us 4. So this is all equal to negative 5 plus 1 plus 10 gives us a positive 6, and 1 plus 1 plus 4 gives us 6, so that's 6 over the square root of 6, which, if we wanted to simplify this down, getting that radical out of the denominator, I'll multiply by root 6 over root 6. So you can see that I just get the square root of 6 for my scalar. So the magnitude of my projection, I know, is going to be the square root of 6. So in order to find what that projection vector actually is, I'm just going to take my scalar and multiply it by my unit vector of v. So finding that unit vector, that's going to be v over the magnitude of v, which we've already calculated our magnitude of v below. That was in the denominator of our scalar, so that's the square root of 6. And my vector v is negative 1, 1, negative 2. So if I'm taking that and multiplying it by my scalar, that's going to be the square root of 6, my scalar, times negative 1, 1, negative 2, divided by the square root of 6. Which, look again, I have more things canceling out. So my projection of u onto v is just going to be negative 1, 1, negative 2. But the neat thing about this problem is that our projection of u onto v is actually vector v itself. So the length and direction that u goes in v is vector v. So if you can envision shining that light perpendicular to v or orthogonal to v, then that shadow is going to completely cover v and not go any further. So that shadow is going to be that same exact length as v in that same direction. And with that, we wrap up this dot product examples worksheet. Hopefully this cleared up any confusion and allowed you to expand upon what you learned in your lesson into your examples. So if you still have any questions, please feel free to leave them in the comments below, and I or one of your peers will respond as soon as possible. So until next video, good luck with your online learning.